So we're going to learn about these imaginary numbers. And an imaginary number happens whenever you take the square root of a negative number. For example, right here we've got the square root of -1. Now typically if you type that into your calculator, you get an error because you can't take the square root of a negative number. If you think about it, like what does the square root mean? It's like, hey, the square root of what, number equals this. Actually, no, let me change it up. If we do have like a -4, this is really asking, hey, what number times itself equals a -4? Right? That's kind of like what we have to figure out. And well, there's no real answer to that, because if I take the number 2, well, 2 times 2 equals a +4. So you say, okay, what about a -2? Well, a -2 times a -2 also equals a +4. So there's no numbers that work. There's nothing times itself that can equal this negative to equal like a -4. That's why we can't take square roots of negative numbers. It just doesn't work. And so some brilliant mathematicians decided that, hey, you know what, we're solving some of these equations, and occasionally when solving equations, they do come up to the point where they have to take the square root of a negative number. And normally they would just get stuck right there. And they said, hey, we wish we could keep on solving these math problems, because apparently that's what mathematicians liked to do hundreds of years ago, just solve problems all day. And they got stuck when they said, hey, I can't take the square root of this negative number. There's no number that exists, right? There's nothing times itself that equals a -1. So what did they do? They said, oh, I got it. Since the square root of -1 doesn't exist, let's make something up. Let's say that the square root of -1 equals I, which is this imaginary number. Notice that I and imaginary, they got that same letter there. So I literally stands for imaginary. So yeah, that's an imaginary number. This is actually the only imaginary number. There's only one of them. And the definition of the imaginary number I is exactly the square root of -1. So this is the only imaginary number, and it is equal to exactly the square root of -1. Now, what the heck is the point of this? Well, if you look at that problem down at the bottom, I've got the square root of -16. Well, normally we'd say, oh, there's no answer. That doesn't exist. We can't take the square root of it because it's a negative number. There's no number times itself that equals a -16. But knowing this new fancy imaginary number, let's make a factor tree for this. And let's separate that out, just like we did when we had simplifying radicals of larger numbers. What if I break up -16 to the square root of -1 times the square root of 16? So we're allowed to do that, right? Because if I multiplied -1 times 16, I'd get -16. So we can do this. But by separating it out into the square root of -1 and the square root of 16, we actually can solve this now. I can get an answer. I can get a number without the radical. Because obviously we know the square root of 16 is 4. But how about on the left side there? I've got the square root of -1. Normally we'd say, well, there's no solution, no answer, or it's undefined. But now it is defined. The square root of -1 is I, this new imaginary number that we just learned about. So when I put those two things together, I'd write my final answer here as 4I. So I is kind of like a variable in a way, except that it's a variable that is always going to be equal to the square root of -1. So here, the square root of -16 is 4I. Pretty awesome, right? I know, imaginary numbers. Who knew? Oh, that's that example I did. So let's simplify the following. On the left, we've got the square root of -20. Well, let's start by breaking it apart. First thing we want to do whenever you see the square root of a negative number is to take that negative out in front and leave whatever we have left over on the other side. Because we know the square root of -1 is definitely going to equal I. Now the square root of 20, we're going to break that down the same way we've always been simplifying radicals. We can say, oh, well, that's 4 times 5. And, well, the square root of 4 is just 2. So we'd make this 2 root 5. And now when we put it all together, we have this I, a 2, and a root 5. The way we would write that is put all the non-radical parts together first, which is the I and the 2. And we always write the numbers first. So we'd write 2I. Then after that, we'd have the square root of 5. So the square root of negative 20 is 2I root 5. Now for this next one, we've got the square root of negative 8x to the 9th. All right. Well, anytime I see that negative, I'm going to kind of separate that and think, oh, that's really like a negative 1 out in front in a way. And so I've got 3 different pieces here. I've got the negative sign, I've got the 8, and I've got the x. Essentially, we're just going to take the square root of each of these separately, simplify each one of those, and then put it all together for our final answer. So I'm going to break this down into the square root of negative 1, and we know that's just going to be an I. And you do enough of these, you're going to realize that, oh, if there's a square root of a negative, I'm just going to have an I in my final answer. But for now, I want to show you exactly what we're doing and how we're breaking it down. Then we have the square root of 8, and then we have the square root of x to the 9th. So just simplify each of these 3 parts separately. The square root of negative 1, we know, is I. The square root of 8, we break down to 4 and 2, because the square root of 4 is 2. So the square root of 8 simplifies to 2 root 2. And then how about the square root of x to the 9th? If I have 9 x's, how many groups of 2 can we make? Since it's a square root, the index is 2. And so if I've got 9 of them, that means I can make 4 groups of 2. So 4 x's will escape the radical, but then you're going to have 1 left over since there were 9 altogether. And 2 times 4 is 9. Or I'm sorry, 2 times 4 is 8, and then there's that remainder of 1, which we have left over under the radical. So now let's put everything together. So all the terms that aren't under a radical come first. There's a 2, an I, and an x to the 4th. Now, since the I and the x to the 4th, the order of those two doesn't really matter because I is not actually a variable. It is this imaginary number. So you can just write it as like 2 x to the 4th I. But if you wrote the I second, that's fine also. And then we're going to have our radical with both the 2 and the x underneath. So this is the simplified radical of the square root of negative 8x to the 9th becomes this down at the bottom. Let me know if you have any questions. Just start talking, unmute yourself, and let me know if you want me to go over anything again. Okie dokie. Now, here's where we're going to get some interesting stuff happening with this imaginary number. And that is when we start combining multiple imaginary numbers, specifically by, well, multiplication. And we're going to get into adding and subtracting them and more stuff like that next week with your lesson, your Edpuzzle lesson on complex numbers. But for now, we're just going to worry about this I, just this one imaginary number. And we're going to look at what happens to it when we raise it to different powers, meaning when we multiply multiple imaginary numbers together, what happens? Because it's something kind of unique. First off, let's look at just I to the first power. Well, just like everything else, anything to the first power is just itself. So if you ever have an I to the first, we just write it as a regular old I. You wouldn't write it as the square root of negative 1. You wouldn't go back to that. It's always going to be, if you have a square root of negative 1, you would write it as I. But now, I squared. Okay, so I squared means we're taking I times another I. Now, to figure out what this would represent, we do want to use that definition of I. We know that an imaginary number is actually the square root of negative 1. Right? That's like this first I. But I'm multiplying it by a second I. So technically, I'm multiplying this by another square root of negative 1, right? Like I times I means the square root of negative 1 times another square root of negative 1. And well, that's kind of nice because we know that any radical times itself, right? Any square root times that same square root, the radicals would actually cancel out. And we'd be left with just a negative 1. Now that's going to be an extremely useful skill right there, that anytime you square an imaginary number, well, that imaginary piece goes away, and we're left with just a negative 1, which is great because negative 1 is a real number. We can work with a negative 1. I is kind of weird. So in your next couple lessons, we're going to be using that property that an I squared turns into a real number. It's crazy. You square an imaginary number, it becomes a real number. It's nuts. All right, what about I to the third? Well, I can rewrite I to the third as simply I squared times I to the first, right? I just kind of separated out that product. If I multiplied I to the second times I to the first, we'd still get I to the third because you add exponents. But I'm going to write it like this, I to the second times I to the first, and use our earlier definitions of I to the first and I squared. We already know what each of those equals. So I to the squared, or I to the squared, I to the second power we know is a negative 1. So I'm going to replace this I squared with just a negative 1. And it is being multiplied by I to the first, and we know I to the first is just I. So when I multiply these two pieces together, negative 1 times I is negative I, which is also kind of crazy. If you cube an imaginary number, it becomes negative. What? All right, one more. I to the fourth power. Well, let's break this apart and write it as I squared times another I squared. Again, using that earlier definition of I squared actually being equal to a negative 1, I squared times I squared is negative 1 times negative 1. And a negative 1 times a negative 1 actually equals a positive 1. And that's the best scenario right there. Because, I mean, I don't know, given the choice between a negative number and a positive number, I think I'd choose a positive one. They're easy to work with. So let me kind of erase these calculations and just write the end result nicely and organized. So I to the first is just I. I squared is negative 1. I to the third is negative I. I to the fourth is positive 1. And so as we increase the exponent, it's just going to change. I, negative 1, negative I, positive 1. Now what happens if we go higher than this? What if I took this as I to the fifth power? This is where something kind of neat happens, where we don't need to worry about any higher exponents than a 4. And here's why. I to the fifth is the same thing as I to the fourth times I to the first. And this is the best part about writing it this way. I to the fourth power, we know if we look down here, that equals a positive 1. So this is the same as just saying, hey, what's 1 times I? And it's just going to be I. So this I to the fourth, essentially we just ignore it because it's just a positive 1. And multiplying by a positive 1 doesn't change a thing. And so, because right here, that's just that 1. It didn't change my value. This was I, and our final answer was just I. And watch what happens as we keep on increasing the exponent. I to the sixth, well, what if we wrote that as I to the fourth times I squared? Do you see this I to the fourth right there? Well, we know that equals a positive 1, and we can just cross it off because it's not going to change our value. Meaning I to the sixth is actually the same thing as just I squared, which we know is a negative 1. And look at this. If we go I to the seventh, Well, we rewrite that as I to the fourth times I to the third. And it happens again. I to the fourth is a positive 1, so we can essentially ignore it. It's not going to change our final answer. So just take out that multiple of 4. And we're left with just I to the third power. And looking back over here, I to the third was equal to a negative I. If we go to I to the eighth, well, we can break that down as I to the fourth times I to the fourth. And well, we know that is actually 1 times 1, which is just 1. And if we look at these 4 different answers, we got an I, negative 1, negative I, positive 1. Those are the exact same answers that we got over on the left, from I to the first, I to the second, I to the third, and I to the fourth. This is nuts. It's like a magic trick. But it's going to actually work out to be pretty nice for us. So this is the same as I, negative 1, negative I, positive 1. Any guesses as to what the next 4 powers are going to be for I to the 9th, I to the 10th, I to the 11th, and I to the 12th? Does anybody see a pattern if you look to the left? Hopefully you can realize that, hey, I to the 9th, we could write that as I to the 4th times another I to the 4th times I to the 1st. Both the I to the 4ths cancel out, and it's the same thing as I to the 1st, which we had over on the left there, I to the 1st and I to the 5th. They're the same thing. So as it turns out, this pattern of just these 4 options are going to continue. So we're just going to get an I, negative 1, negative I, and positive 1. And that pattern will keep on repeating over and over and over again for every exponent of I. So you don't need to worry about multiplying out all these square roots of negative 1. Essentially, you only need to know these 4 options, okay? Because that's all that it's going to be. I to the 3,892 is going to be one of these 4 options. It's going to equal either I, negative 1, negative I, or positive 1. So knowing this, we can simplify these larger exponents pretty easily. So definitely make sure you've got this part on the left somewhere in your notes. You're going to be referring to this a lot, just those first 4 powers of I and those 4 possibilities that it can equal. So let's take a look at simplifying some of these. I times 3I. I'll give you a few seconds to write these down. So these are 3 separate problems, by the way. Okay, so on the left, I times 3I. Well, we treat I just like a variable. Like if I had x times another x, we'd write that as x squared. Well, same idea here. I times 3I is just 3I squared. Now, anytime you're doing any operation with I, it's always going to be able to simplify to one of these 3 options over here. I, negative 1, negative I, or positive 1. Notice that all 4 of those options do not have an exponent. So anytime you see I with an exponent, like in this example right here, we know, hey, wait, we should be able to simplify this so that I doesn't have an exponent. And if you look at that chart that you just created from that previous slide, hopefully you'll recall that an I squared is equal to a negative 1. And so we replace I squared with a negative 1. Then we just multiply. 3 times negative 1 gives us a negative 3. And that's our simplified answer. So I times 3I actually equals negative 3. It's crazy. Those imaginary numbers just go away. All right, how about this middle example? It's a little bit different. It's 6 times I to the 14th. Now we need to think about what I to the 14th would be. Now we could keep on going through that chart that I made on the previous page. We have 1 through 4, then 5 through 8, and blah, 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 and keep going and then figure out what 14 would be. But here's the easy way. You want to think about which number, look at this exponent and think about, is this number divisible by 4? Because like every multiple of 4, right, every I to the 4th, I to the 8th, I to the 12th, those all turn into a 1, and they basically disappear. They go away. And so my thought process here is to think of, okay, look at that 14, and I want to figure out what's the biggest number less than 14 that's also a multiple of 4, because every multiple of 4 we can just ignore. So if I rewrite this I to the 14th as I to the 12th times I to the 2nd. Now, why did I pick 12? Because I know that 12 is divisible by 4, right? That's I to the 4th times I to the 4th times I to the 4th. And I know that all those I to the 4ths just equal a positive 1, which means I'm essentially able to cancel out this I to the 12th. And what we're left with is simply 6I squared. So that 2 is like the remainder after I divide the exponent by 4. So that's another way you can think about it. If you were to divide that exponent by 4, because every multiple of 4 we get to ignore because it turns into a positive 1. Now after you divide that by 4, what's the remainder? And whatever that remainder is, like 2 in this case, that's the actual exponent that we're going to interpret. And if we look at the previous slide, we'll see again that, hey, I squared is equal to negative 1. Multiply these together, and we get negative 6. All right, one last simplification. So this is just a straight up I to the 80th. And we know that every multiple of 4 cancels out. So the first thing that we want to do before I even think about the remainder, like we did over here on the left, is, hey, is this exponent actually divisible by 4? And hopefully you can all recognize that 80, yeah, 8's a multiple of 4, so 80 as well is a multiple of 4. That's actually 4 times 20. And so we actually know that this is going to be a bunch of I to the 4ths times I to the 4ths over and over and over again, 20 times. So you're really just multiplying number 1 20 times, right? So if I do I to the 4th times I to the 4th times I to the 4th, and you just keep doing this over and over, and there's going to be a total of 20 of these, right? And every one of those I to the 4th is just 1, so it's 1 times 1 times 1 times 1, 20 times over. And 1 times 1 a bunch of times is still just going to equal a positive 1. So that's the best case scenario. If you see I with an exponent and you know that this exponent is a multiple of 4, then you can just cross that whole term off and say, oh, that just equals a positive 1. There's very little work to do. So that's your best case scenario. If that exponent is not divisible by 4, then you have to think about, like, okay, well, what number less than this exponent is divisible by 4, and what's my remainder? And that remainder will always either be a 1, a 2, or a 3, which from our previous slide, those are our only options here, right? So it's either an exponent of 1, a 2, or a 3. Because if it is divisible by 4, that's just a positive 1, and we can ignore it. The other scenarios are a negative 1 or negative I, and it will turn into one of these without an exponent. All right, you don't need to write this part down. I just want to kind of give you a little background as to where we're going with these imaginary numbers. Like, why on earth am I ever going to need these? Well, as I mentioned earlier, these types of numbers first came up for solving certain equations where the result would be an imaginary number. And so this is more what we're going to be doing not until after Thanksgiving break. So it's taking the next 2 learning targets together, kind of incorporates this imaginary number. And so here's a nice simple equation. If we wanted to solve this for x, we would first subtract 22. We'd say, okay, so x squared equals negative 25. And then to get the x by itself, we'd have to cancel out the exponent. So I'd take a square root, because that's like the opposite of squaring a number. That means I'd have to square root the right side. And on the left, the square root and the square cancel each other out, and we get x equals the square root of 25. Well, we can't really take square roots of negative numbers, but wait, we can now. That's what the imaginary number allows us to do. So the square root of negative 25 would just be 5i. And so now we can actually solve these equations that have imaginary solutions, which actually solves a lot of problems and allowed math to create the world as we know it today and make things better. Trust me on that. So much fun. But for today's assignment, you're really just going to be simplifying those radicals. Or I'm sorry, simplifying these exponents of I to different powers. And that's it. All right, so try the delta math. It's pretty short tonight. Make sure you get that done. And also, if you haven't done the radical assignment from yesterday or Monday, make sure you get that done today. Very, very important to get that practice in. And then tomorrow and Friday, we're not learning anything new. It's just going to be practice days, okay, to get ready for your test next week. So get the delta math done. And that's it for today. You can all sign off. Have an awesome day. I'll talk to you later.
Mr. Wojcik,
Yeah, what's up, Gavin?
did you get my attendance? Because I joined a little late because my Chromebook wasn't charged. I was joined at like 9:32-ish.
That's fine, Gavin. No worries, buddy.
Okay, bye.
See ya.